So hi, I'm Jeremy Gebben. I work at LunarG, work on Vulkan validation layer performance mostly, which lately means GPU AD. Before that, I worked on mobile for a long time. I was a kernel mode graphics developer, so I crashed your cell phone, and I've also crashed lasers and set-top boxes and satellites. So we're going to talk about validation and what valid usage is, and then walk through a typical error message out of the validation layers. And we'll talk about the debug utilities and configuration. So Charles just completely described what a layer is. Validation is implemented in a layer. The reason for that is kind of a development out of OpenGL, where every driver had to implement all the error checking, and it was essentially the same code replicated across N implementations. And it was always running, which added CPU overhead. And so Vulkan decided that that was inefficient, and we just have it in this validation layer. It'd be enabled for development, but not in released applications. Valid usage is a term from the Vulkan spec, which is what you have to, it's the preconditions for calling a function. The drivers assume that you're giving them valid data. They don't handle most error conditions. Validation does. If you break a validation or valid usage, you'll get undefined behavior. And that undefined behavior will be for the current Vulkan command and for anything after it. So always fix the first error message first. It's just like a compiler error. You get subsequent errors or garbage that are caused by the first one. So undefined behavior is fun. It could be that your application works fine. Could be your output is corrupt. You could hang, your computer could blow up, or you could get rainbows and unicorns. It's also worth noting that including third-party art in your presentation can cause undefined behavior, so instead you get me drawing unicorns. So the VUID is a concept in the validation layers and in the spec. It's just a unique string that identifies an error with great precision, and it's got a format of commands or function and then fields or parameters. It's worth noting that the number is sometimes repeated when a valid usage applies to multiple commands. Draw calls are the most common instance of this, where you have 20 different flavors of draw call, and some of the valid usages apply to all of them. So here's a chunk of the spec for VK create buffer. You'll see there's two sections of the valid usage. There's the first one, unlabeled, which is the rules that are written by humans. Those are pretty complicated, and they're just arbitrary rules that someone made up when they defined the spec. And then the implicit valid usages are very simple rules, like the device pointer must be valid, and those are auto-generated from the XML, and so they're really simple to understand and to validate. So here's two different valid usages. You'll see that they have the numbers and just whatever text the author wanted to put. And the implicit, you have really simple stuff. And all the text on this screen is auto-generated by the spec release tools. So read the spec. That it's huge. It has most of the answers, not all the answers. If it doesn't have all the answers, we can try to improve it and make it better. Got to read this when you're hitting an error. You want to read the section where the VUID is defined, so like that whole create buffer section. And then sometimes you'll have words or phrases in that VUID that are present in the rest of the spec. My favorite is dynamically used, which we'll talk about in a minute. But you can search through the spec and find other discussion related to what you're doing. And then sometimes the VUIDs are split between the command you're using and the structures that are passed as parameters. So except for synchronization 2, there's the pipeline barrier has a massive structure that's passed in, and that has a bunch of rules associated with it that aren't part of the command. So how does a validation of VU get into the spec? There's two ways right now. You can have a new extension, which will define a bunch of valid usage. Those can be in the new commands, or they can be identifying interactions between the new command and some existing concept. And then there's also the possibility of a bug in the spec where someone decides a valid usage is incorrect and we'll make a new one, or just comes up with a new rule where something isn't clear, and some drivers are handling it one way and others are not handling it correctly, and then that'll be a new rule that's needed. The way those get defined is someone makes a pull request to the spec, and then there's a new release of the spec. So like 1.3.234 and then 235 or whatever will have the new rules, and then we'll go implement that in the validation layers. And depending on what is actually defined in that VU, it could take us minutes to do that. Like an implicit VU will be auto-generated. Some things are very trivial and be added in a couple days, and other things take months or longer because they require new types of validation to be developed. And the types of things that we're checking fall into some buckets, which we'll talk about. First one is just straight up API usage. Here's an example where someone's making a 2D image, but they're specifying a depth that isn't 1, and that doesn't make any sense. That's always an error. Then there could be conflicts between what you're trying to do and what the device you're using supports. So you might ask for 5 color attachments, but the device only supports 4. That's an error on that system. Might work on other systems. Vulkan profiles is a tool that you can use to find errors like this. If you have a fancier GPU that supports 16 attachments or whatever, you can run a profile that only supports 4, and then you detect this error on your system rather than the customer hitting it. And then resource constraints are fun. These validation can't completely solve for you. So memory allocation, you can make a completely valid memory allocation call, and it might work on your system that when it's idle, but then you might start up 10 different applications and use a bunch of GPU memory in the background. So this might fail in your application, and it might fail, it might not. Don't know until you run it. And validation can't see this unless you do something like you take that device handle or the device memory handle and it's null and you use it for a different call. Validation could see that, but it couldn't see the original error. So the general rule here is if something returns a VK result, you should handle that and do something sensible with the errors. And so now we'll go through an example where I've modified VK cube to produce an error. Here's the correct code where we're just doing a copy buffer to image, and that ends up making the texture that ends up on the cube. If I hack it to change the row length, the image gets stretched, and that's an error. But the application will still run just fine. You just get bad results, bad output. If you enable validation, you'll get this massive string of stuff, which we're going to go through in detail so that what's going on. The first part is the VUID. So that's the rule you broke. You can just go look that up in the spec right there and ignore the rest of the error message. You might know what's going on. Again, validation has a logging system similar to what Charles described in Loader. So most things are errors. If you enable best practices, you'll get some warnings and performance warnings, but generally you'll just see errors. This message number is for hashing and for detecting duplicate messages. It's generally not super useful. Then you get the real error message, which is, this is the only part of this whole screen that was written by a human, which is we wrote some code to check and we described what we found in that check. So in this case, we're trying to copy too many bytes into a buffer that is twice the size because I changed the row length. And we'll identify which part of the parameters caused the error, and then, like I said, what we detected was wrong. Then we'll have a reference to where in the spec the error is defined. You can click on this link and go read up if you don't want to just put the VUID into Google. The last thing is we have all these object identifiers, all the handle numbers. And so we have a command buffer and a buffer, and they have the exact value of the handle, but no name. And the names get assigned by application developers using this Debug utilities extension. So it lets you define names for your Vulkan objects, for sequences and command buffers and queue submissions. And it also lets you define your own error callback. So if you want to change how that message gets displayed to you, you can do that. The names are also used by other tools like RenderDoc and some other tools besides validation layers also implement this extension and let you set names without running validation. So to add a name, here's the function call. It looks just like any other Vulkan function. The name, the string that you pass in gets copied into the object. You don't have to keep that memory available forever. And so here's what I did in the VK-cube example. I just made a little subroutine that calls the Vulkan call, and I can printf names into the object, or printf into the object names, and have things like the name of the file that's in the texture, which might help with debugging. And then once you have that, you'll see the errors in the log. And then command buffers work the same way. There's an API call. The interesting thing about these is they work like a stack, so you can have multiple labels present on a command buffer at any time. And then the first one printed out is the top of the stack, so that's the nearest to the error. But you could imagine you have a library of code for generating command buffers, and you might not know exactly where you are. So the stack lets you have kind of a nested way to find where the error is in the command buffer. These aren't printed by the default error handler, so this is a good reason to make your own error handler. So once we have all of those labels in there, the error message changes, and we get a little bit of context of where we went wrong. And VK-cube is pretty trivial, but you can go find these labels in the code and get to where the error came out pretty quickly. So making your own message callback, this is the exact same data that the validation layer default message callback gets. So you're on parity with us. And we just print to the console, but you can print wherever you want. You could change the format. You could send it to UI. You could integrate it with your test framework so that a validation error automatically causes the test to fail. The one thing that we don't recommend is using it to filter out messages you don't want. There's a mechanism that we'll talk about in a minute that does that more efficiently. You get these messages after the whole string is built and printed up, so you're wasting a lot of work. And usually when you're dealing with unwanted messages, they're coming out multiple times a frame, and it can really slow you down. So now we'll talk about configuring. Get the SDK, that's the easiest way to get validation. Easiest way, once you have the SDK to enable it, is to run the Vulkan configurator. We'll go through that in a whole bunch of detail. You can also enable it at create instance time. That's great for test frameworks. And then you can also do it from the terminal with environment variables. So Vulkan configurator, there's three main things you want to do. You want to override the applications layers with the top left, and then enable the validation configuration, which is the bottom left. And then the right, you'll have a panel that controls all the settings within the layer. And this, you want to start with a standard preset. So that'll give you all the correct settings to get started without having to go through all of the many different options, which we'll talk about. So like I said, enable it with the VK config. You can also, there's files in the file system for layer settings, and VK config actually writes those. So if you want to figure out how those work, one good thing you can do is set up your configuration with VK config, then go find those files and look at what's going on in there, and then you could save the file yourself and not have to use VK config. There's a bunch of environment variables. There's an extension that you can use, and there's a really good document linked there. That'll explain all of this in excruciating detail. So presets are a really useful feature of VK config. Those are a set of settings that we test, that we recommend. There's standard synchronization validation, GPU-AB, a few others. Those are the best way to start. One thing we see pretty frequently is someone will go in and they'll enable everything they can in validation, and that's going to be slow, and it's not something we test a lot. And the reason it's slow is that each of these different little sub objects is doing its own state tracking, and so as you enable more things, you're doing more and more state tracking, and that can cause some problems. The other thing is that when you're using these presets or any your own configurations, you'll find stuff with sync validation or GPUAB, try to fix it, and then you'll accidentally introduce a more simple error. So you always want to come back to the standard preset or core validation, check that as you're changing your code, and then go back to the more complicated use cases. So we'll talk about some of the individual settings now. Stateless is largely for those implicit VUIDs where it's very simple stuff. Almost all this code is auto-generated. It's super fast. It doesn't track any state, but it doesn't handle very interesting errors. It's just really trivial stuff. Core validation is where almost all of the VUIDs are checked. It has very heavy state tracking, but this is what you want to run almost all the time. This will catch, I would say 90% of the VUIDs are checked by this module. Thread safety is about a section of the spec called the external synchronization requirements. So this is things like trying to write to a command buffer concurrently from multiple threads. This is the module, the object that'll catch that. It has state tracking. It's not terribly expensive. Handle wrapping doesn't actually check any errors, but what it does is it replaces the handles returned by the driver with an integer counter that gets incremented every time you create an object. Drivers can reuse handles as often as they want. And so you could create an image, get ABC as the handle, destroy that image, create another one and get ABC again. And sometimes people will have bugs in their code where they don't notice that they destroyed an image. They have a stale handle and it just happens to work. So this will force you to get that code right, because instead of ABC, you'll get 4 and then 5 and then 6. The other thing that can help is that the handle values from a driver are arbitrary. They could just be pointers. Usually they are. And so you could get random handle values between runs of your application. And this is a little bit more consistent, where a lot of times run the application multiple times and you'll get the same sequence of handle numbers out. And so that can make it easier to compare logs and stuff like that. Object lifetime is a fairly simple object that it's trying to detect use after free bugs. So again, the case of you created an image and destroyed it and then try to use its handle, this will catch it. Whereas the handle might be just a pointer, and then the driver might go and try and dereference it and crash in a strange way that's not obvious, but this will find it quicker. Then we get to the really interesting stuff, which is the shader-based validations. So GPUAB and Debug printf both operate by taking your SPIR-B code and instrumenting it. So adding new instructions around what you were trying to do to either add extra error checking into the shader or add a printf call, which is just not actually printing. It's copying values into a special region of memory that are then post-processed to print them out. Only one of these can be enabled at a time, because we don't want to try to doubly instrument the shader. That gets complicated and slow. They're also not supported on Mac right now, and the reason for that is because of the extra step of going to metal. So most drivers, you go from SPIR-B to a native instruction set. Mac, you go from SPIR-B to metal and then to native instruction set inside the metal driver. And we just haven't, it's nothing in theory that prevents that from working, but it's just more complicated to deal with, and we haven't spent a lot of time on it yet. Sync validation, that's about pipeline barriers and semaphores and fences and stuff like that. John Zuloff's going to talk tomorrow about this area in detail, so hopefully check that out. Best practices, this is performance warnings or other things that aren't specifically errors, but we don't think they're a good idea. There's both common checks and vendor-specific checks. One thing to note is that the vendors are the ones who write their own vendor-specific checks, so we're kind of dependent on them to both provide the checks and to maintain them or update them as their hardware changes. An example for best practices is an undefined value, which is not exactly undefined behavior, but you might get garbage output. So in detail, You might have a vertex and fragment shader. Normal case, you consume all the outputs from the vertex shader in the fragment shader. If you're missing an output and you try and consume it in the fragment shader, that's going to be an error. But if you don't use an output, that's technically allowed, but that could be a mistake. So best practices will say, hey, you're missing this output, or you're not using this output. Are you sure you know what you're doing? Yeah, there's a lot of weird stuff in there, but it's worth a try to see if it tells you anything interesting. One of the best ways to handle all the errors that are coming out and get right to where your code is breaking is this option called break on error. And that'll just trigger an assert, the equivalent of an assert. And if you're in a debugger, you'll get the whole call stack of where you're going wrong. Historically, this worked great all the time, but we're now adding validation that doesn't happen until queue submission time. If you hit one of those errors, you're going to get a call stack for your queue submit and not the command that caused the error. Image layout, sync validation, and timeline semaphores are all places where this happens. We want to improve this by capturing more information about the call side of the error, but that's kind of pretty complicated and also it's going to have performance trade-offs. Here's where you can limit the message severity. Like I said, most everything is error. This isn't the most useful setting, but it's there. The more useful stuff is limiting duplicate messages. So this, like I mentioned, you could get an error message 10 times a frame or 100 times a frame, and you don't really need to see that again after a few. So you can say, oh, I only want to see the first 10 errors, and that'll usually be enough to say, yeah, okay, this is the same piece of code, or all of my code has these different, it's producing the same error. And then you can also disable specific VUIDs here. This is going to happen much earlier in the error output process, so it's going to be faster than post-processing the string yourself in your error callback. And if you're wanting to mute VUIDs, that usually means you think something's not an error. I mean, you could disable something because you think, oh, I don't want to fix this now, I want to see what else is going on. But a lot of times this isn't really an error, or you don't think it is. So when that happens, you've got a bunch of things you can try. You can look at our source code and try and decide if what we're doing to check the VUID is actually correct. Sometimes it is, sometimes it isn't. You could look on Slack or on Discord or Reddit. Talk to Charles on Discord. I hear he likes to solve other people's problems. Just double check that you're understanding what's going on. A lot of times people be really willing to help and can find problems for you. Implicit layers can sometimes cause errors on their own, so you could be getting an error caused by a bad implicit layer. I don't think that's very frequently, but disabling implicit layers is a good thing to try. And if you really think it's a bug in validation or the spec, I mean, file an issue and we'll fix it. Sometimes we don't know ahead of time if it's a validation problem or a spec problem, so just file it with validation, and we know how to move it over to the right repository if it is a spec issue. We also have a backlog. VUIDs get added to the spec very frequently, especially lately. You can see since 1.3, it's kind of the slope has gone up quite a bit. But we've also made a lot of progress in implementing the new VUIDs. So the blue line is going down, which is means we're less incomplete than we were. If you're hitting something that's an error that's in the spec and we're not implementing it yet, file an issue, and that kind of bumps it up. There's, I think, 3,000 or 5,000 or so VUIDs that are currently incomplete. A lot of those are vendor extensions, which again we depend on the vendors for vendor extensions to implement the validation. But if it's a KHR or EXT extension, we can help. And but filing the issue kind of lets us know it's important and bumps it up in priority. And we have quite a few issues. That black line is the raw issue count. It's been going down lately, which is also good. And then these different colors or different labels on the VUIDs. Yellow is incomplete, so that's that's VUIDs that are missing that that need to be fixed. The other colors I don't even remember. But yeah, when we're not busy with issues and new spec releases, we're also working on quite a bit of stuff. One of the big ones is we went through and improved the output for all those error messages. So that human readable string, we've made it a lot more specific about what's going on and can identify which field in the structure has a problem. I've personally been spending a lot of time on descriptor indexing validation, which we'll talk about. Sync validation added the queue submission time validation. Previously it was only within a single command buffer, so that's a big improvement that helps find a lot more errors. We worked a lot on timeline semaphores, queue present, and external memory. One of the bigger ones, which isn't strictly part of validation, is this utilities library. So there's some pieces of the code that we developed that other application developers wanted to use. This format utils header was probably the most common one. These are just things that were coming out of our code generation that were useful in other circumstances. And so we pulled those out into a separate repository so that you could use them without making all of validation be a dependency for your app. Another part of that library is the layer settings library. And that is what vkconfig uses to configure validation. So there's a JSON file format, and there's a library that converts that format into something you can use from your layer to control your settings. So you can have your own layer that works just like validation in vkconfig, where all the settings are present in the UI and everything can be toggled really easily. So that's really cool. If you're a layer developer, I highly recommend checking that out. So descriptor indexing validation is fun. There's this sentence in the spec, which is a big dragon. It says that a descriptor is dynamically used only if the shader invocation uses it. And you could have an array of 1 million descriptors, but only use 3 of them in that specific shader invocation. And unless you run the shader, you really don't know which of those descriptors are used. When I was working on this, I found a shader where they sampled an image and used the value out of that sample to as a descriptor index, and there's no way to figure that out without running the shader. So what happens now is GPU AP has a piece of memory that tracks which of those 1 million descriptors are used. We run the shader, do some basic checks like, is this descriptor still valid? Like if you delete an image, that makes the descriptor invalid. We can detect that on the GPU and prevent a crash, but there's a whole bunch of other stuff that is only checkable currently in CPU time, like image formats and I think sizes or a few other ones. So what happens is we report back to the CPU, here's the 3 descriptors that we use, then we run validation on those after the fact, and that both improves performance and removes the false positives of the other 1 million minus 3 descriptors, which we shouldn't have been validating. If they're not used, they can be garbage, and that can be a ton of extra work. And it can also we also had a mode where that validation would get completely skipped depending on which bindless features you enabled. So it's a pretty big project that's taken a lot of time, and but it has some pretty good results. So this is Doom Eternal has kind of been the benchmark for validation performance for quite some time. The blue line is what core validation was running at. So it's about 2 frames per second. It's kind of painful to watch at 2 frames per second. GPU AV is the red line. It was a bit better, especially once we started using cache memory. Then I moved the descriptor indexing validation to GPU AV. Core validation went way up, became somewhat usable. GPU AV took a hit because it's doing more work. The next big improvement there was we had a wait for idle in the GPU AV code, where after every submission, we wait for idle to post-process. Now we're using semaphores. That brings the performance back up a bit, where they're both kind of equal and marginally useful. Other applications didn't take as big of a hit because they enabled update after bind, or they had a case where we just skip all this validation entirely, so we wouldn't tell you about any of the errors related to descriptors in your draw calls, and that's give you good performance, but would give you no coverage. So now that this is in place, we have less false positives, no skipped validation, better performance. There's still some growing pains, so if you're using this, feel free to provide issues. More test cases are needed, and getting those from the community would really be helpful. So next, we have a lot more work to do in GPU-AV. There's people working on ray tracing. Descriptor buffers is going to be another big project related to the descriptor indexing validation. Sync validation, as Karen mentioned, is working on performance improvements. I'd like to improve the debuggability of these errors that happen at queue submit time. Right now, it can be difficult because you could have thousands of commands that are possible causes of the error. SpearB runtime needs more improvement, and we're going to keep working on that on the message formatting. But file issues, tell us what we can improve on. We do respond. We have a backlog, but we do respond and take those more seriously than things that people aren't caring about. So yeah, validation is complex, or Vulkan is complex. Validation is complex too. There's a lot of rules to follow. When I started working in Vulkan, I was impressed by the VUID system and how detailed it is and how easy it is to find all these errors, even though they exist. And compared to something like Unix command pages, where you kind of just have to grep and hunt around, the VUIDs are a good way to find out what you're doing wrong quickly. Debug utilities can greatly improve your experience with validation, especially for big applications where you have a lot going on. VK-config, again, makes it easy to work with validation. And validation isn't perfect. We want to make it better. Please tell us how to do that. So yeah, the survey is a good way to do that. Issues are a good way to do that. Get a tumbler, tell somebody at the table what needs to be better. So that's it. Any questions?
So you mentioned that we shouldn't probably be enabling every single validation profile in the configurator for performance reasons.
Yeah.
But if I want to do that anyway, is it safe? Could they step on each other's toes?
They shouldn't step on each other's toes, but they might. It's not something that we test explicitly. I mean, we have a limited CPU budget for testing. It's only so much time in the day, so we don't test it. But
it would be just kind
people
of really
do it, and it seems to be working for them. But if you have a real app, like a real game, it's going to be really slow.
Thanks.
So as someone who's working with bleeding edge drivers that aren't even released yet, with new extensions, I'm curious, is there a way to ask the validation layer, or is there a tool or some command to, if I find a particular newish VUID in the Vulkan spec in the newish extension, is there a way for me to ask the validation layer, or check, like, do you check this new VUID yet?
The easiest way to do that is there's a script in our repository called bkvalidationstats.py, and that'll dump out a CSV file that lists everything that we check, if it's got a unit test for it, and a bunch of other stuff that isn't strictly on it.
Thank you.
I was going to say, with each SDK, that script that Jeremy was talking about is run. We create the CSV, an HTML that shows for all the VUs in the spec which ones are validated or not. You will find that in the SDK documentation at vulkan.lunarg.com, the left panel, go to docs, and so you can see for that version of the SDK what's validated or not.
And this graph right here is generated by, it's just a history of all the total counts of each VUID and its status for every spec release. So
the question was made about whether you can turn everything on at once. I think you disclaimed that GPU AV and debug printout can't be turned on.
That's the one.
That's the exception.
Yeah, VK-config will prevent that.
Thought I'd highlight that.
Yeah.
And do all those best practices has own VUIDs as well? the different vendors you said provide the best practices, and they also have the VUIDs for that, or it's
It has a string that it's not a VUID number, but there's a unique string associated with each of those checks. I don't remember exactly what the format of it is offhand, but it does end up with a string in that VUID field. It's just, it won't have a number that's in the spec.
okay.
Just wanted to clarify that a lot of the checks and some of the best checks and best practices won't even have a VUID associated with it. There may not be a VUID in the spec related to that, because VUIDs in the spec are specify exactly how to avoid undefined behavior. And so if your bad practice falls into the category of defined behavior, right, there may not be a VUID in the spec for that.
Yeah, that's a good point.
All right. Any other questions? If not, I guess we'll, oh, got one more here. Hi. You mentioned that a good chunk of the missing VUIDs are from vendor extensions. Are they being a bit lacking there? Is there a mechanism for you to pester them? Do you rely on them? I assume you do.
If it's a vendor extension, we do rely on them, and we do take pull requests, and it's up to the vendor to decide if they want to. Karen, do you pester the vendors about their extensions not having validation?
No, I pester the working group about EXTs and KHRs not having validation. But yes, so the way validation occurs is that a champion for the extension and the working group is also responsible to get the validation developed for that extension. Vendor extensions are ignored. So if you get validation on a vendor extension, it's because the vendor is being very responsible and taking initiative to fill out the validation. LunarG certainly does not have the cycles to go implement validation for vendor extensions.
And to make things more complicated, some VUIDs, especially those related to like external memory, when Vulkan is interfacing with something outside of Vulkan, whether that be an external memory or an external semaphore that's imported, or maybe things with the Windows system you're interacting with. In those areas of the spec, it's not really possible for the validation layer to check every VUID, because to check that VUID would require knowledge outside of Vulkan to validate. And so if you're working in Windows system and external memory, external semaphore area, definitely check the list in the Python script or the SDK HTML to see if that particular VUID is checked.
I think there's a few in dynamic rendering, in the dynamic rendering extension, where we can't check it because it's part of the fixed functionality of the pipeline that we don't have access to. Like, there's a few that are just, there's not a good way to validate them at all. But most of them, it's just there's a backlog and we need time to do it and to prioritize correctly. Anything else? Okay, thank you.